In this lecture, we will state the so-called measure axioms, which give the property of countable additivity of Lebesgue measurable disjoint collection of Lebesgue measurable sets. So this gives us the right framework for talking about a measure which is not only finitely additive for disjoint measurable sets but also countable additive, meaning that if you have a countable collection of disjoint Lebesgue measurable sets, then the measure of the union of all those sets should be the sum of the infinite sum of the measures of the individual sets in the union. So before I state the measure axioms, let me state some notation. So I denote the calligraphic L of Rd as the collection of Lebesgue measurable sets subsets of Rd, and the Lebesgue outer measure M star, when restricted to this collection of Lebesgue measurable subsets, will be denoted simply as M. So which means that if E is a Lebesgue measurable subset of Rd, then M of E is by definition M star of E. So we have already used this notation M of E for the elementary measure and for the Jordan measure, but since M star of E, so this is a remark that since M star of E is equal to ME for any Jordan measurable set, this is one of the results that we proved earlier, that if E is any Jordan measurable subset of Rd, then the Lebesgue outer measure is equal to the Jordan measure of E. So the use of ME for any E in the Lebesgue measurable collection, the collection of Lebesgue measurable subsets of Rd is justified, and it is in fact an extension of the notation used for Jordan measurable and elementary subsets of Rd. So what are the measure axioms? So let me put this as a theorem. These are the measure axioms. So so first, that M of phi equals 0. This we have already seen, that the empty set is Lebesgue measurable, so it belongs to this collection L of Rd, and M star of phi was computed to be 0. So since M of phi is M star of phi, because phi is Lebesgue measurable, M of phi is 0. But see, we have already seen this result, but we are restating it because it will be part of the axioms of a measure when we are dealing with abstract measure spaces. Then it will be part of the axiom. So this was the first part. The second is that if En n equal to 1 to infinity is a collection of sets En in LRD for n greater than or equal to 1, so collection of Lebesgue measurable sets which are pairwise disjoint, meaning that En intersection Em is empty if and only if M is not equal to N. So if they are pairwise disjoint, then the measure of the union n equal to 1 to infinity of En is equal to the sum n equal to 1 to infinity m of En. So since everything here is Lebesgue measurable, we can use m instead of m star throughout. So I'm using both on both sides m of the sets rather than m star. So this second property is known as countable additivity property, and this is one of the most important properties of the Lebesgue measure. And because the Lebesgue measure is a prototypical example of a measure, this axiom will also be part of the axioms for a measure on an abstract measure space. So we will come to that later, and we will just state here that this is the countable additivity property of the Lebesgue measure. This is the empty set property, the first one, and the second one is the countable additivity property. So first one we have already seen, so I'll just prove the second one. So for the proof of the second part, note that, so first note that M of E, so if E is the union, then M of E is less than or equal to this sum of the MENs. So it suffices to show that the sum n equal to 1 to infinity MEN is less than or equal to ME. So we have to prove the reverse inequality. So this inequality was due to monotonicity, countable subadditivity rather than additivity, which holds for disjoint collection of Lebesgue measurable sets. So to prove this second inequality, we observe that if ME is plus infinity, then the inequality holds trivially. Equality holds. Also, if MEN is equal to plus infinity for any n for so let me rewrite this as follows. So if there exists an n such that MEN is equal to plus infinity, then again the inequality holds. Inequality holds because MEN is less than or equal to ME. So this implies that ME is equal to plus infinity, and then we are back to the previous case. So assume that MEN is finite for each n, and ME is also finite. So now I will break up this case into further sub cases. So case 1 is that suppose further that each of the ENs is closed and bounded, which by the Heine-Borel theorem means ENs are compact. So Heine-Borel theorem is equivalent to saying that each of these ENs are compact. So in this case we have that for any n, capital N greater than or equal to 1, the measure of n equal to 1 to capital N En is the sum n equal to 1 to n m of En, because this is the finite additivity property for compact sets, disjoint compact sets. So we have already seen that if so this follows from the following, that if E and F are compact, are disjoint compact sets, then M of E union F is equal to ME plus MF, because E and F are separated. Remember that this means that the distance between E and F is strictly positive, and it follows that the finite additivity property holds. And an induction argument, use induction to then prove that if En n equal to 1 to capital N is a collection of compact disjoint compact sets, then we have n equal to 1 to capital N En is equal to n equal to 1 to n m of En. On the other hand, however, union n equal to 1 to n En is a subset of E, which was by definition the entire union n equal to 1 to infinity of En, which means that m union n equal to 1 to infinity En is less than or equal to m of E, but the left hand side is just the sum of the MENs, and this is for any n greater than or equal to 1. So now take the limit on the left side, to get that the sum n equal to 1 to infinity MEN is less than or equal to m of E. So this implies that ME is equal to the sum n equal to 1 to infinity MEN when all the ENs are compact. Now the next case is case 2, is that suppose that each En is bounded but not closed. So first we had compactness which was closed and bounded, and now I am dropping the assumption that it is closed, but I am keeping the assumption that it is nevertheless bounded. So then since MEN is finite, we have that given epsilon greater than 0, there exists a closed subset Fn inside En such that the measure of En minus Fn is less than or equal to epsilon over 2 to the power n. So I am again using the 2 to the power n trick because I have to sum in the end. So let me put f as the union of all these sets Fn, n equal to 1 to infinity, and this is a f is a disjoint union of closed and bounded sets Fn. Fn is closed, but it is also bounded because each of the En is bounded. So this implies that by the first case that m of f is equal to the sum of mfn, n equal to 1 to infinity, and this is clearly less than or equal to me, since f is a subset of E. So now note that En is a subset of Fn union En minus Fn for each n, of course, and so m of En is less than or equal to m of Fn plus m of En minus Fn, but the second one is less than or equal to epsilon by 2 to the power n by our assumption here. So now we can sum on both sides to get the sum of men, n equal to 1 to infinity, is less than or equal to the sum n equal to 1 to infinity mfn plus epsilon, but this is nothing but the measure of f plus epsilon, and this is nothing but measure of E plus epsilon. So this implies that since epsilon was arbitrary, we have the desired inequality for the case when each Ens are assumed bounded, but they may not be closed. Now a third case is the general case. This is the case when Ens may be neither closed nor bounded. So in this case we can make them bounded by write each En as the countable union of sets En intersection Am, where Am is given by the set of points in Rd such that the Euclidean norm of x is bounded between m minus 1 and m. So notice that this is a measurable bounded Lebesgue measurable subset of Rd. So now this means that MEN is the sum, M equal to 1 to infinity, MEN intersection AM. This is from case 2, where each of these EN intersection AMs, these are bounded subsets of bounded Lebesgue measurable subsets, and disjoint bounded Lebesgue measurable and disjoint, meaning that EN intersection AM intersection EN intersection AM prime is empty if and only if M is not equal to M prime. So we have that the measure of each EN is the sum of all these portions of EN in this annulus region. So now we can write E, this is the union n equal to 1 to infinity, union and M equal to 1 to infinity, EN intersection AM, and again by the second case we get that M of E is the double sum of the measures EN intersection AM. But this double sum, this is a series of positive terms, so it is equal to the repeated sum equal to 1 to infinity MEN intersection AM, and each of these is MEN, so this is equal to the sum of MENs. So this proves that the countable additivity holds for any disjoint collection of Lebesgue measurable subsets of RD. Now let me conclude this lecture with a very useful lemma called the Borel-Cantelli Lemma, and it says that if EN n equal to 1 to infinity is a collection of sets in LRD, meaning that each EN is Lebesgue measurable, such that the sum n equal to 1 to infinity MEN is finite, so this series converges, then the measure of the lim sup of EN, n goes to infinity, this measure is 0. So we know that this is a measurable set, this is a Lebesgue measurable set. Let me just write this belongs to LRD, and the measure of this measurable set is 0. So let's see the short proof. So we know that the measure of the lim sup of En as n goes to infinity, this is the measure of the intersection n equal to 1 to infinity union m equal to n to infinity of Em, and so this is less than or equal to the sum, well first it's less than or equal to m measure of m equal to capital N to infinity Em for any n belong to n, and so this is less than or equal to the sum from m equal to capital N to infinity MEM. So now we will use the Cauchy criterion for the convergence of series. So since the sum m equal to 1 to infinity, the measure of Em, this is a finite sum, so by the Cauchy criterion for convergence of series, we have given epsilon greater than 0, there exists n, a natural number, such that the sum m equal to n to infinity, so the tail of the series is less than or equal to epsilon. So you can choose n high enough so that the tail of the series becomes smaller and smaller, and so the measure of the lim sup as n goes to infinity, En is less than or equal to epsilon for any given epsilon greater than 0, because here we can choose n from the Cauchy criterion and you will have this inequality. So of course this implies that the lim sup is 0, because it is arbitrarily small. This must be arbitrarily small non-negative number. This must be 0.